Hello everyone, I'm Jingjing, and today I'm excited to present our work on expressive piano performance synthesis from music schools. This research is a collaboration between Center for Digital Music, Queen Mary University of London, and National Institute of Informatics in Japan. So let's get started. Our research focusing on music performance synthesis, particularly in piano performance. So our goal is to generate expressive performance from symbolic music representation like MIDI. This process involves two key tasks. The first is expressive performance rendering, which transforms a score MIDI, typically lacking the subtle dynamics, articulation, and timing variations that convey emotion, into an expressive performance MIDI. The second is expressive performance synthesis, which converts these expressive MIDI into high-quality, realistic audio. While most existing work focuses on only one of these perspectives, our works focus on developing an integrated system that addresses both, ensuring a more holistic and natural reconstruction of expressive piano performances. So for EPR, previous work had explored various deep learning models, including RNs, GNs, scans, diffusion models. More recently, researchers have started applying transformer-based methods, borrowing ideas from NLP to improve MIDI tokenization and generation. For expressive performance synthesis, most approaches have relied on differentiable DSP models. However, some recent studies have adapted TTS, text-to-speech models, for MIDI to audio synthesis, leveraging the similarity between generating speech from text and produce audio from symbolic representations. As far as we know, only two studies have investigated integrated system for performance synthesis, and there's no holistic solution to classical piano music. Despite the advancements in EPR and EPS domain, several key challenges remain. First, accurately aligning score MIDI, performance MIDI, and audio is still difficult, making it challenging to build large-scale, high-quality datasets in this domain. This lack of data limits the ability of current models to effectively control expressiveness. And these models are struggle to generalize well, making it hard for them to adapt to different music styles, instruments, or recording environments. To address these issues, we propose a fully integrated system for classical piano performance synthesis. We leverage recently proposed large-scale transcribed piano performance datasets to enhance model training and overcome data limitation. So our proposed system consists of two main models: M2M, a MIDI to MIDI transformer that renders expressive performance MIDI, and M2A, a MIDI to audio neural synthesizer based on text-to-speech models. So the M2M uses a BERT-like encoder to transform score MIDI into expressive performance MIDI, while M2A adapts transformer TTS with hi-fi gain, both from the TTS domain, to synthesize realistic piano performances. The architecture of both models were adapted from previous work, but optimized for the integrated system. First, to enhance performance of the M2A model, we fine-tuned it using a subset from the ATEPP dataset, which contains over 700 hours of diverse transcribed performances. Compared to the originally used Maestro dataset, this dataset offers greater performance diversity and varied real-world acoustic environments. The main difference is the MIDIs in ATEPP datasets comes from the deep learning-based transcription algorithm, while in Maestro, all of the MIDIs were pre-recorded. So our fine-tuning helps bridge the knowledge gap between the Maestro and ATEPP datasets and improves the synthesis quality of transcribed MIDIs. We then propose a baseline system of comparison. The baseline system is a single-stage model, sharing similar architecture to the M2A model, but with school MIDI as input instead of performance MIDI. The training was initialized using the fine-tuned M2A model and trained further with school and audio pairs from the ATEPP dataset. The size of these pairs are limited due to the lack of alignment between school and performance MIDI. And finally, to refine the M2A model, we implemented several enhancements. We adapted octuple tokenization to extract all the filters and choose a lower bit resolution to reduce vocabulary size. 6 filters, as shown in the table, were taken as input, and the model predicts the velocity, duration, and inter-onset intervals to reconstruct the performance MIDI. Besides, we summed the pianist identity embeddings to the final hidden states instead of concatenation for better capturing individual playing styles. Additionally, we refined performance generation by predicting actual note durations instead of deviations, and incorporating probabilistic loss function to increase output variety. We evaluated M2M system using metrics like KL divergence, Pearson correlation, and dynamic time wrapping distance. The results here show that our model effectively reconstructs inter-onset intervals and velocity, but still requires improvements in duration prediction. Additionally, segmenting MIDI into smaller chunks did not negatively impact generation quality. We also noticed that the lower correlation in segments compared to that in full performances, which indicate that the local inconsistency might be ignored or overlooked in full performance assessments. As for M2A model, we use chroma distortion to assess key reconstruction accuracy and MIDI spectrogram distortion to evaluate frequency-wise reconstruction quality. Fine-tuning the M2A model really helped improve synthesis quality. It significantly reduced MIDI spectrum distortion and made the ambient sound more natural. And now compared to piano tech, our model has slightly lower accuracy in key reconstruction. This is mainly because piano tech is DSP based and designed for perfect pitch accuracy. However, our system did a better job at capturing the fine details of expressive performances, which was reflected in its smaller spectrogram distance. We also observed that the current model has difficulty in consistently synthesizing the ambient sound for complete performance due to the design limitation. Finally, we found that the baseline model struggled with pitch reconstruction, likely because it was trained on a much smaller dataset, only 65 hours of data. To further evaluating our system, we conducted 2 listening tests, one for expressiveness, the test A mainly for the M2M model, and one for audio quality, the test B. In total, 13 participants rated expressiveness and 21 rated the audio quality. We used 4 compositions, 2 from the training datasets and 2 unseen to the model, to test the generalization ability for our model. Each was rated on a 1 to 10 scale, assessing how expressive and good the performances sound. The M2M model, as indicated by the subjective listening test results, successfully added expressiveness, scoring higher than original score MIDI, but it's still below human performances as expected. However, when synthesized into audios using the fine-tuned M2A model, expressiveness rating dropped below the piano tech synthesized scores, showing that the audio quality impacts perceived expressiveness. That said, the model generalized well to unseen compositions like Beethoven sonatas, as shown in the figure. For audio quality, results were mixed. The fine-tuned M2A model had lower ratings than original, likely due to the acoustic variability in the ATEPP datasets. While it is better captured the ambient sound, it also inherited noise and imperfection from the original recordings. Finally, our 2-stage system was found outperform the single-stage baseline, both expressiveness and audio quality. It proves that separating performance rendering from synthesis leads to more natural, expressive performances. Now let's listen to some samples so that you can hear the differences yourself. Here, we provided audios into two groups. The first group is targeting to show the differences between the original M2A model and the fine-tuned M2A model. And the second is showing how the human performances in the school MIDI differs from the model we created. I'm only playing 10 seconds here due to the time limitation for the presentation. We could observe obvious quality improvement by fine-tuning this M2A. And now the second group. This output from the M2A model sounds more expressive than the school MIDI. And now let's synthesizing it by our M2A model. You might want to check out more samples on our demo page. In summary, our proposed system successfully enhanced musical expressiveness and audio fidelity, outperforming the baseline model. However, there are still some limitations, such as inability to inconsistently generate the acoustic ambience. So future work, we will focus on improving pattern prediction, try to incorporating chroma loss to enhance the audio quality, and we will also try to enhance performances across diverse musical styles and acoustic environments. Thank you for listening.